Yes, thank you. And thank you for the organizers for organizing this online workshop and having me as a speaker. I would like to talk about some recent research, which is about thermodynamic bounds of mean first passage times in non-equilibrium processes. So let's first go to some common ground, which is first passage times in equilibrium processes. So in this case, we know that there is this Van't Hoff-Arrhenius law, which states that when we have a particle that is trapped in a metastable state, then the average time for it to cross a certain barrier is increasing exponentially as a function of the energy barrier divided by the temperature. So processes are governed by thermal fluctuations over energy barriers. For a non-equilibrium process, what we expect is that the speed of such transitions can increase, but we also expect that there might be a trade-off between dissipation, speed, and fluctuations. This is what we would like to understand better. So let me show you this with a picture. So suppose we would like to somehow know this trade-off between dissipation, speed, and reliability of fluctuations. And more precisely, suppose we have such a three-dimensional space. On one axis, we have dissipation. This is the amount of entropy produced in the system. For example, the amount of heat dissipated in the environment divided by the temperature. Then we have the reliability, which quantifies the fluctuations of the process. And then we have the speed, which is the inverse of the mean first passage time. Then the idea is to find a surface in the space, and the parameters above this surface characterize permissible processes, and the parameters below the surface are non-permissible processes. This is similar to, it's very reminiscent of a second law of thermodynamics. So you see that the permissible processes are the processes that dissipate a lot, they have a large number of fluctuations, and they are slow, whereas the non-permissible processes are those that are fast, they dissipate few energy, and they have very small number of fluctuations, they're very precise. So why would such a surface even exist? Well, the thing is, this trade-off has many faces, let's say, has many examples of such trade-offs. So one example is, for example, in kinetic proofreading. Kinetic proofreading is when there exists a certain protein, a certain enzyme that can bind to a large number of different substrates. And then it has this typical Michaelis-Menten kinetics. But in biomolecular processes, you often want this protein to be very selective to which substrates it binds. For instance, in copying information, you want to have a very low error rate. And therefore, there exists this proofreading step, which is this one. And this is, you can see this as a resetting step. So if the protein has bound the wrong substrate, then it simply resets back to the initial state. So this additional step, it has two effects. So first, it leads to dissipation of energy because this is a flux that appears in the system. It also reduces the speed because you have to reset. And yes, it also increases the reliability of the process. So that's an example of this trade-off. Then this is a more recent theoretical result. It is a very general bound on fluctuations of currents in non-equilibrium processes. It's called the thermodynamic uncertainty relation. In this case, we have a ratio between the variance of a current, this can be, for instance, an electrical current through a wire, divided by the mean current to the power of 2, is greater or equal than 2 divided by the time interval times dissipation rate. So the interesting thing is that this is very general. So it applies generally to non-equilibrium processes. These are two examples of this trade-off between dissipation, speed, and reliability. So let's now go back to first passage times. We want to understand how this trade-off appears in first passage times. So let's go to the, oh, yes, sorry, I had here some. So this is dissipation, the speed, and this reliability. So let's go to the system setup for first passage times. We consider a non-equilibrium process. X can be, for instance, the state of a wire. Then there's a dissipative current, which is the current flowing to this wire. And we consider the first passage time t. So that's essentially the first time this current exceeds a certain interval. There's a positive and negative threshold. And we have it, the current is 0 at initial time. Let me illustrate that. So here we have this current, so it starts at 0. Then we assume that on average it increases, but because of fluctuations, it can as well hit the negative threshold. So we want to know the statistics of the times that this current hits one of these two thresholds. So we get then a distribution for positive, for the times at a positive threshold, a distribution for times at a negative threshold. And then, so this P plus and this P minus are the splitting probabilities. So that's the integral of these distributions and gives us the probability to hit the positive threshold or to hit the negative threshold. So this is more or less the main actors of this presentation, but there's as well thermodynamics. So how do we introduce thermodynamics in such processes? Well, for this, we use this formula here, which is in stochastic thermodynamics is very commonly used. It's often called local detail balance, and states that the entropy production of the process is a logarithm of the probability to observe a certain trajectory divided by the probability to observe a time reversed trajectory. So everything mainly relies on this formula because since we have this explicit formula for entropy production, we can start deriving results. And that's why most results are general, because we start from this formula here. So this appears to be a definition, but in fact, it's not really a definition. If you compute the limit of this quantity divided by time, then for very large times, it converges to the dissipation rate. So it gives us precisely the rate of dissipation into the environment. And this can be shown for many examples. For instance, in this review paper, you can find that. So that's the system setup. So what's then the main result I would like to discuss is the following. Suppose we have this mean first passage time with two boundaries. Then the claim is that this is lower bounded by the ratio of the two thresholds times the absolute value of the logarithm to hit the negative threshold divided by dissipation rate. And then we have here, so what's this? Well, this is simply a statement that this result holds at large thresholds. So we have this remainder term here. This is simply a function that it converges to 0 when the threshold values become very large. This result is, there's no rigorous really proof of that, but there is a theoretical physics derivation based on plausible assumptions. Although the precise regimes of validity, I think, are still debatable. So this is the dissipation, this is the reliability. And then here we have the speed. So this nicely expresses this trade-off between these three concepts. Now can as well think, how do we recover the Van't Hoff-Arrhenius law in this equation? Well, if we look near equilibrium, then we see that this dissipation rate is proportional to this exponential of minus beta, the energy barrier. So in this way, we indeed recover as well the Van't Hoff-Arrhenius law. So if we are near equilibrium, then this bound expresses that mean first passage times are lower bounded by this Van't Hoff-Arrhenius law. That's how we can recover this law. So in what follows, I will illustrate this inequality on a few examples. So let's consider the following simple example. So we have a Brownian particle that moves in a triangular potential. So there is a external force that drives it out of equilibrium. And then here is the width of the potential. So you can simulate this process. So in equilibrium, you see it makes jumps between these valleys. And in non-equilibrium, so if there's a finite force F, then this process X has a finite flux. So it jumps towards one direction. And then, so this X becomes a current, and we can put two thresholds and look at the statistics of first passage times of this position variable X. So if we do that, we get the following figure. So here we have the physical quantities that appear in this inequality. And the inequality states that this ratio must be greater or equal than 1 when the threshold values become large. So that's what the inequality states. And we need, so here we have symmetric thresholds. So we see that indeed that works very well. Although at low thresholds, the inequality doesn't hold, but we never claimed that it should hold at low thresholds, that's fine. So let's then look what happens when we increase the driving of the system. So if we increase the driving, we see that it jumps earlier over the threshold. And when it increases even further, we see that it even works better. So yeah, so you see that in this example, how this bound works when the threshold becomes large, this ratio is larger than 1. So then we can as well compare with the Van't Hoff-Arrhenius law. So the Van't Hoff-Arrhenius law can best be illustrated when you plot the mean first passage time, the logarithm of the mean first passage time, as a function of the inverse of the temperature. And then you should have this straight line. That's how you can visualize that. So here we compare near equilibrium with far from equilibrium. So here, this is the Arrhenius law. So you see that near equilibrium, it works very well because the actual first passage time is the same as Arrhenius law. Whereas far from equilibrium, there is this deviation between the actual value and the Arrhenius law. So let's now compare this with the new result. So you see the new result matches very well to the Arrhenius law near equilibrium. Whereas far from equilibrium, it's a lower bound, so it lies below the actual value. And yes, so you see it represents a lower bound on the actual mean first passage time far from equilibrium. So now what can we do with this inequality? So interesting application is to use this to infer the end production rate from the measurements of these quantities. So if you look on the left-hand side, so if we rearrange these things in inequality, then we see on the left-hand side, we have the end production rate, which in general is inaccessible because it contains the heat dissipated to the environment. And we know the heat is a part of the first law of thermodynamics that is inaccessible, it's a bit invisible. Whereas on the right-hand side, we have a combination of quantities that are easily measurable. We can, if we can track the trajectory of a current, then we can measure all these quantities. So we can use this then to lower bound the end production rate, and in this way estimate the actual value of end production in non-equilibrium process. So this idea is not novel. It has, oh yeah, sorry. So let me first mention that this is interesting because we do not need a model. If you have a model, you can estimate the end production rate by inferring the parameters of the model and then estimate it. But the interesting thing of these inequalities is that you do not need a model to estimate end production rate. So yes, what I want to say is that this idea is not novel. So it has been, for instance, applied with this thermodynamic uncertainty relation. So in the thermodynamic uncertainty relation, you as well have a lower bound, which now is expressed in terms of the fluctuations of the current. But there is so here as well, you have the inaccessible and the accessible part. But there is a problem with this uncertainty relations, which is that if we want to estimate the nth reduction rate, the estimate you get is usually quite low. So for example, here in this paper, it was used to estimate the nth prediction in molecular motors. So that was done for various examples for motors, let's say kinesin 1, KIF17, etc. And you see that so the bound is here too. That's what the bound predicts. You see that the actual value is much larger than the value predicted by the bound. So the bound gives an estimate of about 20% of the actual dissipation rate. So in this sense, this inequality is not so useful because you get an estimate that is too far from the actual value. So then here, these first passage times become interesting because you can show that for this first passage times, if you put the current equal to the nth reduction, then you can mathematically derive that this is an inequality. So that's a quite solid result. It's very general and follows from the fact that the exponential of minus s is a martingale. So you can derive this result. And this is very interesting because it means that these first passage time bounds are tight, and we can then use them to exactly infer the nth reduction rate. So let me illustrate this as well in a simple example. So suppose we have a particle, and this particle hops forward at a rate k plus. It hops backwards at a rate k minus. So now if we plot the relevant quantities, so here in black, we have this ratio that appears in inequality, and you see it converges to 1, and the threshold becomes large. That means it gives you the exact value. Whereas if you consider the uncertainty relation, then you see if thresholds becomes large, there remains a certain gap here. And this gap implies that you can't estimate the actual exact value of the nth reduction rate. So in this sense, these bounds are quite interesting that you can actually get the actual value of the nth reduction rate. So yes, so let me, I guess I'm a bit too fast, but okay, let me discuss the presentation. So here we have discussed this inequality, which is an inequality, generic inequality between first passage times of currents and as a function of the nth reduction rate. You can lower bound this first passage times in terms of the nth reduction rate. And this inequality is interesting for a couple of reasons. So first is that it's conjectured to be generic. So it should apply to stationary systems in the sense that this ratio converges to a constant dissipation rate. So, and then it quantifies a trade-off between dissipation, speed, and reliability. Dissipation is here the nth reduction rate. The speed is the mean first passage time, and the reliability is quantified in terms of the logarithm of the probability to hit the negative threshold in this first passage time problem. And then finally, you could in principle use this to exactly infer the nth reduction rate. And that's possible because the inequality is tight when the current is equal to the nth reduction. So that's all, and thank you for your attention.
Thank you very much, Izaak. I didn't stop you because your timing was perfect. And so now I think we have 5 minutes for questions. So I see some people in the chat. Maybe Gian Maria wants to start.
Yes, thanks, Izaak. Very nice. Actually, I wanted to ask you which assumptions do you need to prove it, apart from stationarity? Do you need the dynamics to be Markovian?
Well, there is one step in derivation which is a bit tricky. which is that you need that the time for the current to reach the positive threshold is the same as the time for the current to reach a negative threshold. And but this, for instance, if the process converges at long time to a drift diffusion process, then it holds. You can so if there's some self-averaging of the processes at long times, because it's a time-extensive quantity, then that should hold. But if I guess the limitations are maybe when you have indeed this very non-Markovian processes, then
Okay.
I think this probably will break down.
Thanks.
Okay, next in the line, Per Francesco.
Yeah, hi, thanks for the talk. I just wanted to ask if you have a generic understanding on how you can saturate the bound. So if there are generic mechanisms through which you can get a bound that is saturated.
Saturated in what sense? You mean?
That you get a strict equality instead of inequality.
Okay. Yes, I think that's you mean for a generic current, right? For any.
Yeah, if you have just generic mechanisms. So if I give you a class of processes, then you can say, okay, they satisfy these properties, so I get a saturated bound.
You mean for which examples of processes the bound is saturated?
Yeah.
So if it's saturated, for instance, for this drift diffusion process, saturated, because it's saturated when J is the end production, and this drift diffusion process, or when the current is proportional to the end production, it's saturated. And in this case, that's the example. The moment that you have many currents, so you have the end production consists of a sum of many independent currents, then if you look at one current, it won't be saturated anymore. And there will be a gap.
Okay, thank you very much.
Okay, thank you. Then I see Gatian.
Yes, I have. Maybe it's I have not understood, but I have a kind of provocative question, because if I understand well, you look at when a current crosses a threshold to measure a current, but then you already have the result.
You mean?
Because you are looking at the current, which means that you are able to look at it.
So that, so I don't get exactly. So you mean?
So when S equals J, and you were showing this graph when you have the currents that grows up to a threshold, if you are able to monitor this current to measure itself through a bound, there is a kind of contradiction.
So you mean to estimate the end production rate, right?
Yeah.
Yeah, so you have to, I get your point. So you have to optimize. You have to somehow compute this. So if you look at the bounds, right? Yeah, so you can compute these quantities for any current, but you don't know its end production. Then you minimize that. You try to find the current that minimizes this combination of quantities. And since you know that it's tight and the current is equal to the end production rate, or the current is equal to the end production, if you minimize this problem, you find eventually end production.
Okay.
Does that make sense?
A bit more. Okay. But this thing is, it means that you are able to look at several currents if you have to minimize looking for one current. So then it means that you can look at several currents.
Yes, you must be able, yes, if you want, but even if you have several currents, in general, you don't know the affinities.
It's a linear combination of currents that gives you some reproduction. So maybe you can look at currents, but you cannot look at forces. That's what you mean.
You have to know, yes, if you want to measure the end production, you need to know the affinities.
Yeah, as well. That's true.
And if you
sometimes you don't know them if you don't have the dynamics. That's true.
The system.
I agree. Okay, get it.
Okay, so let's maybe take the last question from Francesco.
Yeah, so probably it's related to the previous question of Gianmaria. So if your P minus is difficult to estimate, So let's say your L minus is far away compared to L plus, so it's a rare event you need to estimate. So that expression is very difficult to convert to give you anything meaningful. No, you have a logarithm of a small number divided by a large number. And...
Yeah, that's really a drawback. That's asymptotic bounds. So you have to be able to compute this P minus. I think in practice, you compute it for different thresholds and you fit it to an exponential. So you would do it, but yeah,
what I don't understand is that can I just relabel everything? I don't know. Is there something? Maybe I'm not understanding well the expression, but I could relabel. Let's say I have the L plus close, L minus far. Can I relabel everything and still get a reasonable estimate?
No, that doesn't. No, you need both thresholds to be far. It doesn't work. You see, you have here the minimal threshold.
I see.
If one threshold is close to 0 and one other one goes far away, that's not sufficient. Then it doesn't work.
Okay, thank you.